Alright, so this is my lab 4, the rope physics spring mass lab. The objective of this lab was to analyze the motion of a spring mass system in which the mass swings on an arc while oscillating on the spring. This lab was examined by applying two main principles with the momentum principle and the energy principle. The motion was analyzed using the tools tracker and VIDLE, and the results from this lab ultimately showed that the spring mass system does indeed satisfy the energy principle, and the predicted motion of the mass followed the same pattern as the data received from tracker.
One of the principles applicable to this lab is the momentum principle, where the change in velocity is equal to the net force divided by the mass times delta t, as shown here. The other principle is the energy principle. The energy principle is the total energy of the system, which is equal to the kinetic energy plus the gravitational potential energy plus the spring potential energy. How it is applied specifically is explained later.
This is the video that was placed in tracker. The calibration state was placed to represent the relaxed length of the spring. The origin is where the spring was attached, and after tracking the motion, the x and y values were placed in the CSV file that would then be used with the code. This is the code constructed via VIDLE. The initial conditions are indicated at the beginning with the mass of the ball, the initial position of the ball, the initial velocity of the ball, and the start time. This part of the code takes the position values we saved earlier. The following equations were used to solve for the spring constant, the change in stretch, and the stretch length of the spring. Such values were placed into the code here. The omega period equation resulted in a spring constant of 5.94 newtons. The relaxed length was found to be 0.0361 meters, and this part of the code calculates the length of the spring at each time interval. Now for the system's energies. The energies that are present are the kinetic energy, gravitational potential energy, and the spring potential energy. First, the initial energies are assigned to these variables. As the system moves, however, the value of these variables change. The net force, as shown here, is the spring force, which is Hooke's law, and the gravitational force, which is mg in the negative y direction. It should be easily noticeable now where the momentum principle comes into play. The new predicted velocity of the spring system can be found with the net force. The position is then updated as a result when the velocity changes at each time interval. In this section of the code, the spring is updated. The position of the spring changes, so does the stretch or compression, updating the computational model. Finally, the new energy of the system is updated at the time intervals. All three energies have to be recalculated. The changes are stored and then plotted at each time interval. When the code is ran, this is the model that comes out. The red ball is representative of the data from tracker, and the blue ball is representative of the computational model. It can be seen they follow a similar path. The blue arrow is the spring force and the black arrow is the gravitational force. The model can be seen drawn here.
The graph here shows the position data in the y direction. As you can see, it is close to the computational model and accurately matches the motion of the graph. There is a slight discrepancy, however, but this is because eventually the drag force catches up with the spring force. And as always, there is round-off error from the calculations done throughout the lab.
A graph was also constructed showing all the energies in the system. The blue line represents the change in kinetic energy, the red line is the change in spring potential energy, and the green line is the change in gravitational potential energy. The yellow line is the sum of the energies, which we all know is 0. Now let's answer the lab questions. For the what does it mean question, the energy principle is satisfied. The work done by the surroundings is equal to the change in energy. But because the mass, spring, and earth make up the system and nothing in the surroundings, then work equals 0. And work equals the change in energy. And on the graph shown here, the change in energy is the yellow line, which is 0, if you can see closely. In response to lab question 2, these are the two oscillation graphs. The period of oscillation for x is 1.6375 seconds, and the period of oscillation for y is 1.52 seconds. There is a difference of 0.1175 seconds. This is due to the fact that each equation has different values. For the y direction, the equation for oscillation is based on mass and stiffness, and in the x, it is based on length and gravity, causing such a discrepancy. Overall, it takes more time to move a cycle in the x direction than a cycle in the y direction. This concludes Lab 4.